In this video, we're going to talk about VSEPR theory. VSEPR theory is a theory that allows us to make quick and reasonable predictions about the shapes and bond angles of molecules based solely on the information contained in the Lewis dot structures. So you don't have to actually do any sort of experimentation with what's called X-ray crystallography, where you beam X-rays at a molecule and watch how they bounce off from the molecule in order to determine its shape. Instead, simply by looking at the formula of a molecule and then drawing its Lewis dot structure and looking at this particular combination of lone pairs and bonding pairs around the central atom of the molecule, you can quickly come to a reasonably accurate determination of what it must look like. Okay, so let's take a look. VSEPR, or pronounced VSEPR for short, stands for valence shell. That means the electrons in the outer valence shell, the outer electrons, electron pair repulsion. So electron, basically that means that the electrons that make up the outer shell repel each other when they are arranged around the central atom. And again, the repulsion that we're going to be concerned with is only from the electrons that are around the central atom. The outer atoms' lone pairs have absolutely no effect on molecular shape. Now you can see that right in the middle of the screen. It was so important that I actually highlighted it and put it right in the middle of the screen, just so you could see. So bonding pairs and lone pairs repel each other. Creating as large of an angle as geometrically possible. The reason for this, of course, as you know, electrons are negatively charged. Therefore, their like charges repel always. That is the fundamental rule of chemistry. Well, actually of all nature. Like charges repel, opposite charges attract. Every single thing we do in chemistry, from here until the time you finish chemistry, even if you major in chemistry, you are never really doing anything else but accounting for the repulsion of electrons for each other and the attraction of protons and electrons. Everything else is just the way that that happens. So bonding pairs and lone pairs of electrons repel each other. Lone pairs are even more repelling. Why is that? The reason that might be is because lone pairs, unlike bonding pairs, don't have positively charged nuclei on the other end of those electrons. When you have a bonding pair of electrons, they're sandwiched in between two atoms, and those atoms contain offsetting positive charges in their respective nuclei. Lone pairs, however, do not bond another atom. Therefore, you have fewer protons for those electrons to reduce or dampen the effect of the negative charge. So lone pairs are sort of like naked, bare negative charge. And so that negative charge repels even more because it's not offset by any positive charges coming from any other nucleus, from another atom or any other nuclei. So as a result, because they repel so much, they actually squeeze the bonding pairs together. They squeeze the other bonds in the molecule together to get away from those lone pairs. This is the reason, and you'll see in a moment what I mean by this, but this is the cause of the inequality signs in the trigonal pyramidal and the two different bent geometries. The lone pairs are always responsible for the less than symbol in any bond angles. And you'll see that. Afterwards, come back and reread this section, and this will make more sense to you then. If it's a little premature now, don't worry about it. Just keep it in mind. Okay, so I'm going to repeat this because it's so important. Only the central atoms pairs of electrons determine the shape of the overall molecule. So the outer atoms may have lone pairs all around them, like fluorine, for example, being an outer atom, may have a bunch of lone pairs, but those lone pairs have absolutely nothing to do with the shape of the molecule. Only the central atom, only the central atom's lone pairs matter, and the combination of bonding pairs and lone pairs. So for example, no matter how many lone pairs fluorine or chlorine or oxygen or whatever has, they don't matter. Only the central atom's combination or different groupings of electrons affect the shape of a molecule. Also, how do you count groups of electrons, or how we're going to often have to count or number how many different or separate groups of electrons. Even though VSEPR stands for electron pairs, oftentimes multiple pairs are going to make one single group. For the purpose of counting the different groups or different directions of electrons, a double bond and a triple bond, the electrons in that double bond and triple bond are a single group. So the 4 electrons that make up a double bond are a single group or a single counting. You count them one time, or a single direction of electron repulsion. Likewise, the 6 electrons that make up a triple bond are just one group. They are not separate groups. Because they all fit together as one group and they are in one direction, they are only one group. Lone pairs are also counted as each a separate group. So each lone pair is by itself. So you can never mash together 2 lone pairs and say, oh, these 4 electrons are one group. It doesn't work that way. Lone pairs are not like bonding pairs. They are not in one direction. They are pointed in different directions. The molecular geometry of a molecule is the shape of the molecule. The shapes have specific names. Now, just like in geometry, regular geometry, you name shapes according to the shape that you see. So a square has 4 sides, a triangle has 3 sides, a rectangle has 4 sides, but not all the sides are equal in length. Well, there are special names for molecular geometry. There are special names for the shapes. The 6 shapes that we're going to look at each have their own name. On top of it, each shape has its own associated bond angle. That's the angle that 2 outer atoms and a central atom make. The molecular geometry of the shape is named according to the arrangement of the outer atoms around the central atom. So it's that arrangement of atoms, but the lone pairs are not going to be part of the name of the shape. The name of the shape isn't going to be based on where the placement of the lone pairs. That doesn't mean the lone pairs have nothing to do with the shape. They have a huge impact on shape, but their effect is indirect, and we don't name the shape after the position of the lone pairs, only atoms. The lone pairs will cause the atoms around the central atom to arrange themselves in a particular way. The resulting shape of those, an arrangement of those atoms, is how we name the shape. So let's just jump into some examples here. Well, actually, before we get into examples, let's actually talk about the names and bond angles. These are the 6 different shapes and their associated bond angles that we are going to look at. I've also put some shorthands here. These shorthands are not by any means universal, and they do not stand for particular elements. A and B are simply fillers. I could have put X and Y. I could have put W and Z. I could have used any letter or symbol I wanted. I just chose to use A and B for stand-ins for elements. So A stands for the central atom, and B stands for any outer atom and all the outer atoms. Whether they're the same element or different elements, it doesn't really matter right now for the purpose of talking about geometry or molecular shape. The lone pairs are represented by a colon, because my keyboard does colons very well, but doesn't understand lone pairs. Okay, so A is the central atom, B is one or more, actually two or more outer atoms. These are the 6 shapes that we're going to talk about. These are not the limit, by the way. There are about 6 more geometries beyond these 6 that you will take a look at in a future chemistry class, but not in this class. In this class, we are going to limit ourselves to simply the 6 basic geometries, although there's really nothing basic about them. It's simply a way of dividing up the subject, that's all. So you're not overwhelmed. There's nothing, the next ones aren't really any more difficult. They have a few extra concepts to think about, but for the most part, it's the same concept, just extended even further with more groups of lone pairs and bonds. Okay, so the first example is linear. Linear, look at the word linear. Linear stands for line. Linear is just a way of describing something as line shaped, just like planar is describing something that is flat. So linear, a linear bond angle is 180 degrees because a straight line is 180 degrees. This is 180 degrees across. As usual, I didn't plan my shapes very well, my spacing very well here. 180 degrees. A straight line is 180. So this is a linear shape. A linear shape will always have exactly the same arrangement of lone pairs and bonding pairs, or you could say it this way, lone pairs and bonds around the central atom. You will have a single central atom. Well, you always have a single central atom. You will have only exactly 2 outer atoms, and you will have no lone pairs on the central atom. This is a necessity. Everything here that you see about this is absolutely required. You must have exactly 2 outer atoms, no more, no less, and you must have no lone pairs on the central atom. If any of these conditions are not met, then it cannot be a linear molecule. It must have exactly 2 outer atoms attached to a central atom, and the central atom must not have any lone pairs. Now you might ask, well, what about double bonds versus single bonds versus triple bonds? Doesn't make any difference at all. Remember, a triple bond is the same number or same number of groups as a single bond. It's the number of outer atoms. It doesn't matter how they're bonded to those atoms. Even though technically we are looking at lone pairs and bonding pairs of electrons, you're going to be a lot better off if you simply count the number of outer atoms bonded to the central atom and the number of lone pairs instead of counting actual electrons. So whether it's a single bond B, or a double bond B, and we're going to see examples of all these, or a triple bond B and single bond B, it makes absolutely no difference. In all three of these cases, we have 1, 2 groups, or in other words, 1 atom, 2 atoms. 1, 2, 1, 2. We only have 2 groupings. A triple bond is a single group the way a single bond is. A double bond is a single group of electrons, just like a single bond is. And like I said, you can simply look at the number of atoms, and that's probably going to be better for you in terms of counting the number of quote unquote bond pair groupings to consider. So as long as you have two atoms, two outer atoms, and no lone pairs on the central atom, you have yourself a linear molecule, meaning a molecule that has a 180-degree bond angle. Bond angle just measuring from outer atom, so outer atom to central atom to outer atom, 180 degrees. Okay, how about the next one? Trigonal planar with a bond angle of 120 degrees. All trigonal planar molecules have exactly 3 outer atoms. They have 3 outer atoms, and again, no lone pairs on the central atom. And it's only the central atom's lone pairs that we care about. Remember that. We don't care about the lone pairs on the outer atoms. Whether they have them or not doesn't affect the shape at all. So we draw the shape like this. There's a 120-degree bond angle. So 120-degree bond angle. In other words, when we measure the angle, say we start from this point here, we draw a line here, and then we draw a line out to here. So outer atom to central atom to outer atom again, that angle measures 120 degrees. And no matter which sets of outer atoms we measure, the bond angle will always be the same for all the bond angles in the molecule. So whether I do that B and that B, or I do maybe a different one, maybe this, this, and this, that's still 120 degrees. If I try the other two, let me pick a different color other than green. How about, let's go with bright red here. Again, this bond angle is 120 degrees. So you can see every bond angle is 120 degrees. That's why this is listed as 120. We have 3 outer atoms, 1 central atom, no lone pairs, again, on the central atom. Do the B's, the outer atoms have central atom? Do the outer atoms have lone pairs? Yeah, maybe they do, maybe they don't. It doesn't really matter. In fact, some could, and maybe others don't. Or maybe they have different numbers. Some might have 3 lone pairs, some might have 2 lone pairs, and the other one might have no lone pairs. It makes no difference. Trigonal planar is made up of a central atom with only with 0 lone pairs and only 3 bonding pairs or groupings of bonding pairs. How about double bonds versus single bonds versus triple bonds? Doesn't make any difference. In fact, you'll see many different kinds of arrangements of double and single and triple bonds, and even different resonance structures can be drawn for different molecules, depending on the central atom. So for example, I could have a double bond to this B and single bonds to the other, or I could have all double bonds. Doesn't change anything about it. These are still both trigonal planar. By the way, it's not triangular, it's trigonal planar. Please memorize or remember the correct names of these things. Learn to name things correctly to avoid confusion and to help your memory. Trigonal, trigonal means 3 corners. The reason it's called trigonal, in case you're wondering, is because, I mean, I hate to say this after I just told you not to call it triangular, but the truth is the shape does kind of resemble an equilateral triangle. Another thing you can see, that wasn't a bond, that is simply me drawing the basis of the shape. The names of the shapes come from the way they look. Another thing you can see is if I were to draw a circle around this atom and put the central atoms in the center, the direct center of the circle, what I would have is I would have each atom located at points along the circle that are exactly 120 degrees apart. 120 degrees apart. Well, we know that a circle is 360 degrees. So if I divide up that circle into 3 slices, I get 120 degrees. that, not coincidentally, is our bond angle. The bond angle is the result of dividing up the space around the central atom into 3 even areas. Why? Why is it doing this? Because the electrons in these bonds are repelling each other. They're trying to get as far away from each other as possible. And the only way they can do that is to spread out as much as possible. Why 120? Because if they try to go any further, if these electrons try to get away from these electrons by moving further, they will only end up closer to the other pair of electrons. This is the compromise that they all must reach to maximize the bond angles for all of them, to equally split up the space among all 3 groups of electrons. Now you might wonder, what if they come out of the plane? What if it's not planar? What if one of them sticks out into the z direction? Let's say, for example, this is the y direction, and this is the x direction. What if they try to go out into the z direction? It doesn't matter. 120 will still be the maximum. You can try it for yourself using whatever geometric methods you want. You'll see that you cannot place 3 different atoms around a central atom in any way where they will not be where they will be greater than 120 degrees separated from one another. To move them in any other way just brings them closer to another pair of electrons. Okay. So the next one is the tetrahedral shape. Tetrahedral, tetra means 4, hedron means sides or sided. So a tetrahedral shape, tetrahedral molecular geometry is going to be a 4-sided figure, or it's going to create the outline or the corners of a 4-sided figure. And the bond angle associated with that is 109.5 degrees exactly. An ideal tetrahedron has bond angles of 109.5 degrees. All tetrahedrals have exactly 4 bonds to them, or 4 atoms around the central atom. And again, no lone pairs. No lone pairs around the central atom. And we don't care about the lone pairs. Whether there exist lone pairs or not around the outer atoms has no bearing whatsoever on the shape. But the central atom has no lone pairs and 4 atoms around it. So we have A, B, B. I'm going to draw something called a wedge and dash shape. The wedge and dash, this is called a wedge. Wedge. The wedge represents the atom coming out of the page, or out of the screen in this case, at you. So the wedge is pointed outward, out of the screen. That's what it's supposed to represent. A dash represents, this is a dash. Let me write that a little bit neater for you here. Maybe if I use capital letters and I don't make my D look like a P. Dash. A dashed line represents the atom behind the screen. So it's going backwards to the back of the screen. The regular lines here simply represent bonds, or the atoms are in the plane of the screen. So here we have the picture of a tetrahedral molecular geometry. The bond angles, so any bond angle is measured. If I take B to A to B, that bond angle is going to be 109.5 degrees exactly. This is in the ideal situation where all the outer atom, the B outer atoms, are arranged equally, meaning the volume of space, the 3-dimensional volume of space around the A is evenly divided between all these B outer atoms. They will end up forming 109.5 degree bond angles. Why is it called tetrahedral? Because the shape overall forms a shape that looks like a four-sided pyramid, a four-sided figure. Tetrahedral. These are imaginary lines. These are imaginary. But if I were to draw a sort of connecting line to each of these outer atoms, what you would end up seeing is something that looks like a pyramid, but we're not going to call it a pyramid. That name is actually reserved for a different molecule. We end up drawing a tetrahedron, a four-sided figure. Where are the sides? Well, here's one side, two side. The back is the third side, and the base is the fourth side. So, and the A here is floating inside. It's floating in the center of the tetrahedron, not touching the floor, but not touching the ceiling either of the pyramid. Well, it looks kind of like a pyramid. It's just sort of hovering in the middle of this imaginary, and it is an imaginary. These shapes are named based on what they look like, or what the skeleton of the shape would look like if it were delineated by the outer atoms. So this is called tetrahedral because it is shaped like a tetrahedron. So you need exactly 4 outer atoms, and you must not have any lone pairs to make a tetrahedral shape. Okay. Now, so far, all the bond angles have been their ideal, meaning I didn't warp the bond angles with lone pairs being extra repulsive. All the bonding pairs, whether double bonds, single bonds, triple bonds, doesn't matter. All the bonding pairs are sharing the space around the central atom equally. So all the bond angles are their ideal, meaning they're perfectly split or divided amongst the different atoms. Lone pairs are not like that. Lone pairs are very repelling. They're more repelling than bonding pairs. So the electrons that make up lone pairs are going to shove aside the bonding pairs. They're going to shove aside the bonds, and hence the atoms that are bonded, the outer atoms that are bonded to the central atom by those bonding pairs of electrons, are going to be pushed together. They're going to be squeezed together. Lone pairs squeeze bonds closer together because they repel them even more. The bonding electrons would rather be closer to each other than closer to a lone pair, because a lone pair, remember, is a bare naked negative charge. No dampening or offsetting positively charged nucleus at the other end of a lone pair. A lone pair is kind of like a dangling bond. It's a pair of electrons that never bonded another atom. So it never brought in another nucleus with its set of protons in order to dampen the negative charge around it. So our very first one is going to be the bent shape. Bent, also called angular, though I'm always going to use the phrase bent. I will always use bent. I don't say angular. Why use 3 syllables if you can get away with 2? There are 2 kinds of bent shapes, by the way. So these have the same name, but they are different because their angles are different. One is a narrower angle and one is a wider angle. Let's go with the narrower angle. Let's go with the wider angle first. Bent. So bent with a bond angle of less than. Now the less than symbol is only there when you see lone pairs. Notice that the inequality sign is only used when there's 1 or more lone pairs, again, on the central atom. We never care about the lone pairs on the outer atoms. They have absolutely no effect. Did I say that enough times? I don't know. Only the lone pairs on the central atom count. So if there are 1 or more, if there's even 1 lone pair, you end up with an inequality sign on the bond angles because you are warping the ideal bond angle by reducing it. And it's always a less than symbol. That's because the bonds end up getting closer together, so the angle between the atoms gets smaller. So the bent shape with a bond angle of less than 120 is due to the lone pair on the central atom. So our central atom has exactly one lone pair to get the bent less than 120, exactly one lone pair. And then you have bonds to the two outer atoms. Again, to get a bent shape, you can only have exactly two outer atoms. You can't bend a shape. You can't make a bend with more or less than two if you have outer atoms. If you have less than two atoms, you don't have any kind of a shape. You simply have if you simply have this isn't a shape. You could say it's linear, but that's not linear either, because linear is made up of 3 points. So you must have exactly two outer atoms, a total of 3 atoms, but exactly two outer atoms and only exactly one lone pair to make a bent less than 120. Why is it 120 or less than 120? Think of it this way. What is this type of bent shape? All this bent shape is a trigonal planar molecule. It's a trigonal planar molecule that just happens to be missing that top bond. That's all it is. Trigonal planar was 120, so a bent with only one lone pair. Think of it this way. The lone pair substituted or subbed out the atom that would have been there. Remember, a bond to an atom is made up of exactly 2 electrons. The lone pair is simply the bond without the atom. Well, if you don't have the atom, then you don't really have a shape. The shape's names are determined by the arrangement of atoms, not the arrangement of electrons. So because I'm missing the atom up that would have been up there, I end up instead with a shape that is not trigonal planar with 120-degree bond angles, but bent. And what about the angle? Well, again, this lone pair is more repelling than a regular bonding pair. That's because, again, no outer nucleus to diminish that negative charge. So because it's more repelling, it squeezes the 2B outer atoms, it squeezes them together to make a bond angle that is, well, we don't know. Here's the thing. When I say less than 120, that's not a number, is it? We just know that it's not going to be 120 because of the lone pairs. They're going to squeeze it. They're going to squeeze it to something less than 120. How much less than 120? We don't exactly know. And indeed, it will actually be different for different central atoms, different molecules. So we don't exactly know how much less than 120. That's why when you don't know something in science, you don't make up something. You don't make up numbers if you have no basis for them. That's the difference between science and, I don't know, business. You don't make up the numbers and then go to jail for embezzlement. We don't exactly know how much less than 120 the bond angle is. So because of that, we simply say less than 120. Now, if we wanted to know exactly what the bond angle is, we'd have to perform an experiment called X-ray crystallography. X-ray crystallography, like I mentioned earlier, is when you shoot X-rays at molecules. When you get a bunch of molecules, usually in the solid state in a powder form, sometimes in liquid form, and you shoot X-rays. You basically take X-rays of molecules. Those X-rays hit the molecule. The X-rays hit the molecule and then bounce off. They reflect off. And then you capture the X-rays, you record where the angle that the X-ray made when it reflected off that molecule. And based on the information from the angle at which the X-rays bounced off from all the atoms that make up the molecule, you can figure out the bond angles and even the bond lengths of the molecule. And therefore, you'll have its shape. Well, X-ray crystallography is great, and nowadays it doesn't take that much time. However, you are not going to go and do that. You instead are simply going to use the proper, valid Lewis dot structure to make quick estimates and fairly good estimates, predictions about the shapes of molecules. It's a lot easier to draw a Lewis dot structure of a molecule than it is to run an X-ray crystallography experiment, especially since I don't think you have an X-ray machine lying around your house. So that's why we use this technique. Yes, there are real experimental ways to determine this information. And the Lewis dot structure is a good, and the VSEPR theory that uses it to predict these shapes is just an approximation, but it's a pretty handy one. It's sort of like a back of the envelope calculation. You don't necessarily want to crunch the numbers at exactly when you do that. Well, likewise, you don't necessarily, maybe you just need to know when something's bent or linear. Well, bent or linear, this is a good way to quickly figure it out by drawing a Lewis dot structure, something you can do with a napkin and a pencil, and you can figure it out. Notice, by the way, the bent shapes and the linear shapes all involve exactly 3 atoms, 2 outer atoms and 1 central atom. So these may be difficult to distinguish. Likewise, the trigonal planar and the trigonal pyramidal or trigonal pyramidal also have 3 outer atoms just like each other, so they're hard to distinguish. The only one that you should never ever have any actual trouble with is tetrahedral. Tetrahedral will always be obvious because it is the only molecular geometry that involves having exactly 4 outer atoms. No other shape shares that in common. Every other shape is either 2 outer atoms or 3 outer atoms. Only tetrahedral has 4 outer atoms, meaning only tetrahedral has a total of 5 atoms. You have no other shape. If you have a molecule with 5 or more atoms in it, you have no other choice than to pick tetrahedral as the molecular geometry. So at least you've got that going for you. Between trigonal planar and trigonal pyramidal, the only difference between them, of course, is the presence or absence of a lone pair on the central atom. And between linear and one of the bents, again, the difference is between the presence or absence of lone pairs. So there are all kinds of little tricks to help you remember. Just if you see these kinds of patterns, just recognize them and allow them to help you. But think of it this way, lone pairs take up the same or more space as the atom would have taken up, but they are not counted as part of the name of the shape. You ignore them, you pretend they're not there when you're looking at the shape and trying to figure out what shape does it best resemble. This looks like, so you took a rod or metal bar or something and you simply bent it. That's why it's not called trigonal planar, because there is no third item up here. The presence of a lone pair does not mean you have a third group. You do not. Not for the sake of naming the shape. Of course, the shape was determined by the lone pair. If that lone pair weren't taking up space up there, then these 2 outer atoms would have been free to become linear instead. But the reason they're not linear is because that lone pair is emanating negative charge, pushing them down. So the lone pairs do dictate the shape, but then when you name the shape, you name it according to what you see, and you only see atoms. And X-rays, by the way, only see atoms. X-rays do not interact with lone pairs. In fact, it's debatable whether lone pairs are a physical reality. They're more conceptual than real. Sort of like orbitals, but even less realistic than orbitals. Okay, I'm just going to clean up this a little bit here. Okay, so the bent shape with only 1 lone pair is wider. So you have 120-degree angle. 120-degree angles. That's because it's derived from trigonal planar with 120 degrees. What about the other one, the less than 109.5 bent? The less than 109.5 bent derives from, you can think of it as this way, derives, quote unquote, derives from tetrahedral. Think of it this way. Imagine a tetrahedral shape, but instead of having an atom, you simply have lone pairs, but you still have the rest of the molecule still looks exactly the same as the tetrahedral I drew earlier. So you have your, I meant to make a dash here. Let me try that again. Sometimes it seems digital ink runs just as much as real ink. Okay, so you have your wedge and dash here. Now here, instead of having that atom up here, there's no atom, just a lone pair. Nevertheless, the lone pair still has negative charge and still repels the other ones, the other atoms, so they still stay in that same shape. So they still stay away. In fact, they're squeezed together to make a bond angle that's less than 109.5. The tetrahedral shape has an ideal bond angle of 109.5. Because the lone pair squeezes the bonds, squeezes them together to get less than 109.5. How much less? We don't know. And it's okay, we don't have to know. We're not going to make up a number. We're not going to guess when we have no basis for guessing. All we're simply going to say is we know for sure it must be less than 109.5 because we know that the lone pairs never, they have an effect. They never cause an increase in bonds. They only cause a decrease because the lone pairs can only squeeze the bonds together. So we have a bond angle, BAB. If all the BAB bond angles are less than 109.5. This is called, I'm sorry, I'm drawing the wrong thing. I jumped to the trigonal pyramidal shape. Why did I do that? I'm so sorry. We're still working on bend, aren't we? Sorry, let me, sorry about that. I don't know why I suddenly started thinking about trigonal pyramidal. Let me redraw that. The same logic is going to hold, by the way, between bent less than 109.5 and trigonal pyramidal. But let me, I don't know why I did that. Here we go. So bent less than 109.5 has two. It really is derived from the tetrahedral shape. That everything I just said is still true. So bent less than 109.5. So instead of having a tetrahedral with two atoms here, B and B, these are gone, and instead we just have these lone pairs, these loose lone pairs. Because of that, two lone pairs, think of it this way, two lone pairs repel more than one lone pair. As a result of that, you get more, therefore, you get more squeezing, more squeezing together. Two lone pairs are going to crush together the B's, the outer atoms here, even more, so that you get not just less than 120, but less than 109.5. Another way to think of it is, since these derive from a tetrahedron, 1, 2, 3, 4 different groups of atoms around the central atom, since they derive from a tetrahedral, but we know it must be less than the bond angle of a tetrahedral, then it must be less than 109.5, not simply less than 120. So more lone pairs, more squeezing, smaller bond angle, less than 109. Fewer lone pairs means more wide angles, less than 120. Or consider this, which shape do they derive from, or which shape do they have something in common with? Well, the bend that has two lone pairs is more similar in a sense to the tetrahedral because you have 4 groupings, 1, 2, 3, 4 groupings of electrons around the central atom. Well, 4 groupings around the central atom is it results in a tetrahedral arrangement. But when you name the shape, you realize, wait a minute, it may be a tetrahedral arrangement, but 2 of those are not atoms. So we don't name the shape according to them because we can't see them. Indeed, again, our X-rays can't even see them. The X-ray will only see something that is this shaped. And this is not a tetrahedral because you need something that looks like this to be tetrahedral. So this shape is bent, but it's bent in the sense that the bond angles are narrower because of all that repulsion from those lone pairs, that extra super repulsion from lone pairs. Now the trigonal pyramidal has the same exact logic behind it, only this time, again, you're taking a tetrahedron with a trigonal pyramidal. you're taking the tetrahedron, but instead of removing two of the bonds, you're only removing one of them. Let's say, for example, you remove this top bond, and all you have instead is just that lone pair without the atom. So then you have atom, 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 A in the middle. So what shape do you have now? Now you have trigonal pyramidal less than 109.5. Again, just like a tetrahedral shape, it had a 109.5 degree bond angle, but because this negative charge repels so much, it's going to squeeze these bonds together. And when it does, you get a bond angle that is something less than your starting point of 109.5, something less than the ideal angle of a tetrahedral. But you don't know how much, and you don't guess. You don't try to guess the number. It is absolutely wrong to simply figure out what the number is and type it in. Because you can't, you have no basis. Unless you have experimental data behind you, you cannot form an opinion about the number. It could be as low as 90 degrees. Why is it called why is it called trigonal pyramidal? Let me draw it a little bit better so you can see. And let me clean up this area just a bit. So why is it called trigonal pyramidal? Well, you'll see it looks very much like a pyramid. I'm going to use a wedge and dash diagram again. So the B up front, and you're going to see better pictures than this in the upcoming examples when we go through them. I put the pictures in on the next slides. So you have a B coming out at you. This one is from the screen itself. You have a B going back behind the screen. And then, of course, you have your lone pair, which are not named as part of the shape because you can't pretend you can't see them. All right, and let's go with this. So when we draw the shape, we start at the only atom at the very top, and we draw a shape like this. And we just connect all the outer atoms and the central atom, and we end up with a shape that looks very much like a pyramid. We get a pyramid shape. And yes, it is a tetrahedron. Personally, I think this should have been called the tetrahedral shape, and the other one should have been called the pyramid. The other one looks more like a pyramid to me than this does. The difference here, of course, is that you have a lone pair rather than an atom. So you kind of have a shorter tetrahedron, and a shorter one because you don't have an atom up here, right? There's no atom up here, so there's no B up here. So the pyramid ends up being shorter. So the shorter tetrahedron is the pyramidal. Pyramidal, meaning shaped like a pyramid. And that's why it's called that. It's a short pyramid. This time the central atom is at the top, at the apex of the pyramid. In the tetrahedron, the central atom is in the middle of the pyramid and one of the outer atoms is at the top of the pyramid. That's the difference. So just to distinguish them, we'll draw it again. Remember, these lines are imaginary, right? These are imaginary lines that I'm drawing on the outside. They are not bonds. They are simply imaginary. Just to help you imagine the shape. If it doesn't help you, then don't worry about it. And forget about the shapes and just remember the names. Darn it. So there's the difference. Central atom on the very top with a lone pair sitting on top of it. That's a pyramid. Central atom in the very middle with an atom on top at the apex. That's a tetrahedron. That's the difference. Okay, let's actually look at some examples. Okay, so our first example, again, we're gonna go in the same order. Example of a linear shape, carbon disulfide. Carbon disulfide, so carbon and then sulfurs on the outside. Carbon disulfide would be linear shaped, 100-degree bond angle. So we have 6 electrons, 4 electrons, 6 electrons. That's a total of 16 electrons. So when we draw this, we draw carbon, sulfur, and since we've already talked about Lewis dot structures, I'm not going to spend too much time talking about them again. If you need a refresher, go back to the previous video and notes. But I will just go through this process quickly. So we have our carbon and our sulfur. We have our lone pairs to make our, to give each of our elements an octet, like that. We see that we have 16 electrons, but this has 20 electrons. 8, 8, 8, 6, oh, whoops. There we go. Now it has 8. 8 on one side, 8 on the other side. That's 16, 18, 20. And the 18 and 20 are the 2 lone pairs on the carbon in the middle. So we have a total of 20 electrons. 20 electrons, of course, is bigger than 16 electrons. So we have to fix this. And we fix this by creating double bonds. So we take sulfur, double bond to carbon, and then we do the same thing on both sides. I know I have to do this twice because I know I overshot the number of electrons by exactly 2 pairs. So I know I'm going to have to create 2 double bonds. Every time you create a double bond to reduce the number of electrons in your diagram, in your structure, you're going to remove 2 electrons net. Well, I know I need to remove 4 electrons, so I'm just going to do the same thing twice. That leaves me with 2 lone pairs on each of my sulfurs. Of course, you know, this structure also has resonance, but I'm going to draw the more stable resonance structure, the major resonance contributor here. So this is my Lewis dot structure for carbon disulfide. 2 double bonds. So how many groups of electrons do I have? Or in other words, what pattern does this actually represent? Either way, you can see it either way. Well, I have 1 group and 2 group, 1 and 2. Or you can think of it this way, I have 2 atoms and no lone pairs. Now you might say, what do you mean no lone pairs? You've got like 1, 2, 3, 4 lone pairs. Remember, no lone pairs on the central atom. And that's the only place where they have an effect on shape. No lone pairs on the central atom. And I have exactly 2 outer atoms. I should have said 2 outer atoms, right? Or 2 grouping. You can either count the number of atoms or you can count the number of groups of electrons. Remember, a double bond is a single group of electrons. A triple bond is still just 1 group. You count them in groups or directions of electron repulsion. So because of that, this is clearly linear. This matches the AB2 with no lone pairs. If you go back, you can see linear is a central atom with 2 outer atoms and no lone pairs. That's exactly what we have. So if you draw a valid Lewis dot structure that ends up having a central atom with no lone pairs on it and only 2 outer atoms, that is definitely 100% linear. Those are the criteria. And so this has a 180-degree bond angle, and it looks like we drew it correctly with the correct shape. We drew it in a straight line. So for example, it would be absolutely wrong. It would be wrong if you were asked to draw the shape of the molecule. It would be absolutely wrong to draw it like this. Now, if you're only asked, if your only intention is to draw a Lewis dot structure, then this is okay. Lewis, okay, but wrong shape. Lewis dot structures predict shape, but they themselves are not meant to be representative. The Lewis dot structure sort of theory or model is not meant to display shape. So wrong VSEPR shape. So if your goal was to draw the correct shape, it would be absolutely wrong to draw this. Even if it's a perfectly fine Lewis dot structure, it would be a very wrong VSEPR structure. And now that you know shapes, you should always draw them correctly. For your own sake, for your own benefit. I'm just saying for you, I can't see what you're doing, but for your own practice and your own understanding of molecular structure, you should do that from now on. So we have a linear shape. Notice the two double bonds doesn't have anything to say about whether it's linear or not. Single bonds, in fact, if you look at these down here, try these other examples, try all of these, try these other examples. And I've listed for you exactly which examples match which combination of single, double, or triple bonds. Try these other examples on your own. Make sure you come back to these particular arrangements or configurations of the bonds. Beryllium chloride, hydrogen cyanide, silica. This is, by the way, quartz, silicon dioxide, or it's one allotrope of quartz. And the what's called the, I should have put the name, the azide ion. Azide ion. Azide is not one of the ions, the polyatomic ions. I'm going to recommend that you memorize. If you want to memorize it, go for it. It's a very highly reactive ion, and it is useful for certain purposes. Anyway, it's called the azide ion, but it's not on your list of ions polyatomic ions to memorize. But if you want to memorize it, you can. There's no harm. The more you know, the better off you are. So try these other examples. I'm not going to walk through them here, but give them a try. Let me know if you have any trouble coming back to either the arrangement, but all of these are linear molecules, despite the fact that some are single bonds, some are composed of triple and single bonds, and of course you see a double bond. This double bond here, by the way, two double bonds has very much the same structure as here. Also very much the same structure as carbon dioxide, which we have already seen. So try that one again. Draw it on your own, but we've already done carbon dioxide. We did that at the end of the previous video about Lewis dot structures. Okay, let's move on now. Now here's some one example and some other suggested examples at the bottom. Try these. Try these as well. I have given you a hint as to what they will look like when you are done drawing the Lewis dot structures and then put them in the proper geometry. These are the particular arrangements of the double and single or double and single bonds for these particular items. We have formaldehyde, which you've already seen before. I believe we did this in a previous video. We have borane, which we may have done a similar molecule to this. It slipped my mind at the moment. The nitrate ion is one of the polyatomic ions that you need to memorize its formula and charge for. And sulfur trioxide, this is not a polyatomic ion. This is a neutral molecule that is often confused with the sulfite ion. But the sulfite ion has a 2 negative charge. This has a neutral charge, therefore it is a molecule, not an ion. Okay, but let's do boron trifluoride. Boron trifluoride is going to have the same shape as borane, or BH3. That's because whether you have outer atoms with 3 lone pairs each, like fluorine, or outer atoms that have no lone pairs, like hydrogen, it doesn't affect the shape, because only the central atom affects the shape. I'm only going to say that like maybe 4 or 6 more dozen times, and then I'm going to stop. Okay, so BF3. So quickly, we'll just run through the Lewis dot structure. I have boron bonded to 3 separate fluorines, like this. Each fluorine has 3 lone pairs in order to make an octet. We know that boron does not require an octet, but can get along fine with a hextet or a sextet, one or the other. sextet, hextet, something like that. Boron is just fine with 6 electrons, so we don't need to do anything else. Do we have the right number of electrons? Well, let's see, we have 3 plus 3 times 7. That's going to equal 24 electrons, and indeed we have 8, 8, and 8. You know fluorine has to have 8, so each one of these fluorines is 8. That's 24 electrons, so this is a good structure. All the fluorines have their octets. Boron doesn't need an octet, but does need a sextet at least. So this is a good Lewis dot structure. Again, notice we have this conforms or comports with the AB3, the single central, and this, ironically, in this case, A is B, and B is F. I hope that's not too confusing. In other words, there's a single central atom. We have a single central atom. We have no lone pairs on that central atom, but we do have 3 outer atoms. That makes for a trigonal planar. Remember, planar means flat. This is a flat molecule, laying flat on its back. You can put it on a flat surface and all 4 atoms will touch the surface at the same time, simultaneously. And again, you can see there's a triangle. Again, the triangle is just there for imaginary triangle. Imaginary triangle. Also, you have an imaginary circle. Imaginary circle encompassing all of these. So you have, whoops, what made me do that? You have 120 degrees, 120 degrees, and 120 degrees. I probably didn't draw it perfectly at 120-degree bond angles, but it's supposed to be ideally 120. You're splitting up a 360-degree circle into 3 even slices, making a Mercedes-Benz sign, 120 degrees apart from each other. Those are the bond angles. So it's boron, 3 fluoride, boron, 1 boron and 3 fluorines. So a single central atom with no lone pairs with 3 outer atoms. And the rest of these are all examples, but just again with different configurations of the bonds. But remember, double, single, or triple bond does not affect shape. It's just the number of atoms on the outside. Or you can count it in terms of the number of groupings. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. A double bond is no more than a single bond. A triple bond is no more of a group than a single bond is. Doesn't matter how many electrons you have in a bond, it is still one direction of electron repulsion. In other words, you have repulsion going out this way, you have repulsion going out that way, and you have your repulsion going out that way. I don't want to get too involved with these arrows though, because we're going to use arrows to talk about something completely different in the next video, where we'll use arrows to represent something called dipoles. Anyway, I recommend you draw the Lewis dot structures and then predict the shape for each one of these as practice. But each one of these should yield you a trigonal planar shape, molecular geometry, despite how different they are, some of them being ions, some of them being molecular compounds. They all yield the same shape. And remember, carbon is always central. And if there's a central atom, all the other atoms are bonded directly to the central atom. So the oxygen is bonded to the carbon, and the 2 hydrogens are also each bonded to the carbon. They are not bonded to each other. If they ever are, I will make it very obvious to you. I will stipulate it. So 120-degree bond angle, trigonal planar, 120-degree bond angle. If you notice, all the molecular geometries, all the names of the shapes have unique and specific bond angles associated with them. Even the 2 shapes that have the same name have different bond angles, less than 109.5 versus less than 120. Okay. I thought I'd include some pictures with these only because of their 3-dimensional nature. We're getting out of flatland here, and we're going into more 3D sort of arrangement. So I just thought I'd give you a little bit nicer of a picture here. This is what's called a ball and stick diagram. ball and stick. This one right here, ball and stick diagram. You can kind of see why. I don't think I need to explain that. So the central atom here is in this example, carbon is of course the central atom, and hydrogen, the outer atoms are all hydrogen. Remember, by default, carbon is always central. Even if there's any ambiguity, carbon gets to be central, unless you have a very good reason otherwise. The bond angle is 109.5 because this is a tetrahedral molecule. Tetrahedral always has exactly 109.5. And here, of course, you have your wedge and dash diagram. Wedge and dash. Not as pretty as the other picture, I admit, but I did the best I could. Wedge and dash structure or diagram, you decide what you want to call this. Again, we have our carbon. By the way, typically carbon is supposed to be represented as black in any kind of model. When molecules are modeled, carbon, the standard color for carbon is black. The standard color for hydrogen is white. The standard color for oxygen is red. The standard color for nitrogen is blue. And the standard color for any halogen is, I believe it's green. So halogen's green, carbon is black, oxygen's red, hydrogen's white, nitrogen is blue. And roses are red and violets are green. Anyway, so methane, CH4. So if we were to draw this, again, I'm using the simplest molecules in the examples just so we can arrive at the shape rather quickly. However, please pay attention to the also tries. I highly recommend you go through these other examples and let me know how it goes with you if you have any trouble at all. These are very good examples to go through for two reasons. Number one, some of them are a little bit more complex, involving multiple different sorts of arrangements of the bonds, meaning a mix of double and single bonds. Also, they are, in several cases, they are the polyatomic ions that you are going to have to memorize. So at least drawing them will sort of help you to keep them in mind and remember them. Perchlorate ion, phosphate ion, and sulfate ion are all on your list of polyatomic ions to memorize. That's coming up in Module 5, by the way, if I didn't mention that yet. You can see that in the list of things to memorize in the check-in module, where I listed the kinds of things that need to be memorized, including the polyatomics ions list. And I also mentioned that it is Module 5 where you encounter that. But don't wait until Module 5. It might be too late by then. So you might prefer instead to get started early, especially if brute force tedious memorization is not your thing. Okay, so you can kind of see the 3D arrangement here, right? You can kind of see this hydrogen sticking out. This hydrogen corresponds to this hydrogen right here. This hydrogen in the back, well, this hydrogen corresponds to this one. This one in the back, I guess this is sort of a mirror image. This one corresponds to the one in the back, and then this one, of course, corresponds to this one up here. So dash, wedge, in the plane of the screen, in the plane of the screen. So carbon, methane, and I want you to remember the name of this molecule, methane. It's so common. This is natural gas. This molecule is everywhere around us. Some city buses actually run on natural gas. Some cars, well, not so sure about how many cars run on natural gas, but natural gas also is the gas that if you have a gas stove at home, you are using methane gas. That's natural gas. So we have CH4. We have carbon and 4 hydrogens. That's 4 electrons plus 4 times 1 electron for each hydrogen. That's a total of 8 electrons. So we have carbon in the middle. We have hydrogen. Now, if I just draw it like this, I'm going to do something different. This time I'm going to draw it incorrectly. So I draw it like this, and I'm done. I have 2, 4, 6, 8. 8 electrons equals 8 electrons. So this is a good and valid Lewis dot structure. Totally valid Lewis dot structure. But dead wrong for shape. Why? because this shape is supposed to have 109.5 degree bond angles. Instead, this shape has 90-degree bond angles. None of the shapes we are going to cover in this class have 90-degree bond angles. So that is wrong for the shape. Perfectly valid Lewis dot structure, terrible shape. No shape that we learn in this class. Now, there will be shapes that you look at in the future, but no shape in this class, unless I've changed my mind. No, I haven't. No shape in this class will have 90-degree bond angles. That is too close. That's the problem with that. Too close together. The electrons in these bonds don't have to be so close to each other. If there is any room at all for the electrons to spread out, they will spread out to achieve what? 109.5. Why should the electrons be only 190 degrees close to each other when they can be 109, when they can spread out even further, diminishing the electron-electron repulsion between those different bonding pairs of electrons? That's the reason. They do that. The reason you might draw this like this with 90-degree bond angles is because you draw it in a plane. You'd maybe imagine a circle, 360 degrees divided by 4 equals 90. Here's the thing though, nature is not limited to a circle. It's not limited to the flat plane. It's not limited to 2 dimensions. Nature knows that, hey, I can escape this by coming outward. I can't draw outward, I'm sorry. Anyway, so instead of being flat, one of these hydrogens can stick out of the plane and another one can go back behind the plane of the board or of the screen. And you end up bending and wrenching this out of the 90-degree bond angles to get 109.5. You might object and say, well, wait a minute, earlier you told us that this thing couldn't ever be more than 120. That's true, but that's just a physical reality. If you try to bend these out into any other shape, if you try to take this fluorine and bend it out of the plane in an attempt to get more than 120 degrees, you're going to fail. Even if you manage to separate this fluorine, and I don't believe you could necessarily, but even if you manage to get it a little bit more than 120 degrees, all that would end up happening is you'd end up getting it further from one by 120, but getting it closer to the other one by less than 120. Unfortunately, I'm not a master geometer, and this isn't a geometry class, so I can't prove it to you, but the fact is 120 really is the maximum for trigonal planar. However, in other words, the planar arrangement is the maximum, but for the tetrahedral, arranging 4 different atoms around the volume of space surrounding the carbon, you don't have to stick to planar. There is a way to increase the distance, the angular distance between the outer atoms by placing them in a 3D tetrahedral configuration. And nature will do that. No one has to tell it to do that. The electrons will repel until they reach a compromise where the repulsion from one set of bonding pairs is equal to the other, and then they aren't pushed any further. So don't do this for tetrahedral. 90-degree angles are always wrong in this class. 109.5 degrees for tetrahedral. That is the only acceptable angle for tetrahedral. Not less than, exactly equal to 109.5. Let's continue on. I'm using is sulfur dioxide. This is actually the sulfur equivalent of ozone, which we looked at earlier. Instead of the oxygens on the outside, you have sulfur. But remember, sulfur is in the same group as oxygen, so it really doesn't make any difference. It doesn't change anything about either the Lewis dot structure or the molecular geometry, other than that you're replacing oxygens with sulfur. So earlier we saw that ozone, sorry, let me redo this. Ozone had a double bond on one side and a single bond on the other. Well, here we have sulfur. Just replace the 2 outer oxygens with sulfur, and it is exactly the same thing. Same exact thing. Same number of lone pairs, same distribution of bonds and lone pairs. Everything is the same because sulfur has the same number of valence electrons as oxygen because they are in the same group. You can always predict that. You can rely on that fact. So SOS, sulfur dioxide. And if you are breathing sulfur dioxide, indeed, you do need help. Get away from there as soon as possible. This is a poisonous, toxic gas. So sulfur dioxide, now the question is, why bent? Why not linear? Why not linear? It looks like a linear molecule. I just drew it as a linear molecule. This is a perfectly valid Lewis dot structure. Why not linear? Because you're ignoring the fact that lone pair, well, I mean, not you, I just mean in general, anybody who draws this linear is ignoring the fact that these lone pairs are repelling. In essence, you've got these bonding pairs right up against the lone pairs. That's too close for comfort. These bonding pairs, you don't have just two groups, you have three groups of electrons, and they all want to get as far away from each other as possible. You have one group, two group, three group. The way to separate three groups of electrons around a central point is to put them 120 degrees apart from each other. Think of it this way. Imagine it like this instead. Imagine it like with an oxygen in the middle, draw a circle around the oxygen, put the sulfurs out here 120 degrees apart from each other. And even though this isn't technically true, now remember, I'm going to draw something here for illustrative purposes only. Lone pairs do not have bonds. Lone pairs are electrons. You cannot bond lone pairs, right? A bond is two electrons. You can't connect to a lone pair of electrons to an atom by throwing another two electrons at it. This is just for illustration purposes, but I'm going to put the lone pairs up here as if they are sort of like another bond. But remember, they are not a bond, they are a lone pair. What do you get? Well, you get 120 degree separation to put these things evenly, to spread these things evenly around a circle. Okay, so why is the bond angle less than 120? Because lone pairs have negative charge, which emanate through space, repelling even more than regular bonding pairs. Repelling, extra repellent. I'm just going to say it one more time. Lone pairs are extra repellent or extra repulsive. If that helps you remember it, even better. Or extra repellent. Either way, repulsive or repellent, they push more. So because of that, you end up with these bonds moving away from the lone pairs and squeezing to become something less than the ideal angle of 120 degrees. So that's why this cannot be linear. The presence of a lone pair means you cannot possibly have a linear molecule. The presence of a lone pair on the central atom means you can't, because you're dividing up that space into three. A linear molecule only divides up the space in two. Well, dividing a circle into two even slices gives you 180 degrees. That's fine. But dividing a circle into three gives you 120 degrees. And because it's not an even sharing, because lone pairs take up more space in a sense, you end up with a bond angle that is less than 120 degrees. Also, try ozone, try the nitride ion, which is again one of your polyatomic ions to memorize, so it's worth looking into. The boronide ion is not one of the ones you have to memorize, but give this one a try as well. Again, different ions will result in may result in different combinations of double or single bonds, or they might be the same, but it's just more practice for you. So again, perfectly valid Lewis dot structure that we started off with here. Remember, Lewis dot structure, if somebody or if you simply really caring what the shape is, then this is a perfectly valid answer to that question. Perfectly valid Lewis dot structure. Perfectly valid Lewis. But terrible to separate shape. need is the Lewis dot structure, then you don't have to think about the shape. But if you want to know, if you want to draw or you need to know the correct shape, then you must go one step further and look at the combination of, look at it this way, look at the number of different groupings of electrons around the central atom, whether they're lone pairs or bonding pairs. Double, single, or triple bond doesn't make any difference. It's just still one group. Lone pairs, though, are always counted individually. Here's the other bent. Remember, it's even narrower than the 120. Why is that? Narrower than 120 because more lone pairs squeeze more and take up more space for both reasons, actually. Both of these are good reasons. Actually, the space taking up thing is actually even more important. Remember, these lone pairs are not just sitting on the oxygen doing nothing. They are emanating out negative charge. And because of that, you essentially have a tetrahedral. It's sort of like you have invisible legs of a tetrahedron that you aren't going to count when you actually name the shape because you won't be able to see them. You see their effect, you don't see them. So you see the effect. You see the effect of lone pairs, but not the lone pairs themselves. So you don't name the shape according to what you cannot see. And I mean that literally, in a sense, literally, when you use X-rays to look at molecules, the X-rays do not show lone pairs. They only reflect off of atoms. So you only see the atoms using X-rays. But the lone pairs are there affecting the shape because they push those atoms around by virtue of pushing around those bonding electrons. So you see the effect of lone pairs, but you do not see the lone pairs themselves. Therefore, you get a bent shape rather than there's something called an electronic geometry, which is the so-called geometry of the different groupings of electrons around the central atom. Personally, I don't find much value in that theory. So I don't really teach it or emphasize it in my class. I don't care if you know about electronic geometry or not. It's not a worthwhile concept in my opinion, because it is not realistic. Electronic geometry is a concept that gets you into the habit of thinking of lone pairs as being actual physical objects that can be spotted through an X-ray, through experimentation. It is not. Again, lone pairs are not actually, they're more of a conceptual framework or part of a model of understanding molecules. Where their actual existence is debatable, and it's mostly comes down to the math behind the Schrodinger equation, if even that. So I don't emphasize electronic geometry. I know that some of my, sometimes I put out practice homework or practice worksheets, I should say, that ask about electronic geometry. You know, you can skip those if you want. It won't affect you as far as I'm concerned. It will not affect your understanding of the material. So if you see electronic geometry questions, feel free to skip them. You're not going to lose anything. You're not going to lose any kind of critical understanding or conceptual framework. In my opinion. They might be pedagogically useful for you. If they are, then great. But if they are not, then just go ahead and ignore them. I do. All right. So water. Water, of course, is very important to us. Water, we have 2 hydrogens plus 1 oxygen together. So that's 2 times 1 electron for each hydrogen plus 6 electrons. Again, that gives us 8 electrons. H2O. So oxygen is in the middle because there's only 1 oxygen. And we put the hydrogens actually here. We put the hydrogens on either side of the oxygen, like that. Now, if I draw it like this, I also have to put lone pairs on the oxygen to give it an octet. The hydrogens, of course, should never, ever, ever receive lone pairs because they have a maximum of only 2 electrons. So 2, 4, 6, 8 electrons, that checks out. Valid Lewis dot structure. Remember, you can only make these predictions from valid Lewis dot structures. Lewis dot structures are very important because you cannot make accurate, or You cannot make good predictions about VSEPR shapes, valence shell electron pair repulsion theoretical shapes, without a valid Lewis dot structure to start with. So this is a valid Lewis dot structure, but again, this is a terrible, terrible shape. Water is not linear. If water were a linear molecule, life as we know it would not exist on Earth at all in any shape or form. Linear water is a vapor, is a gas at room temperature. Linear water at room temperature would have none of the properties we associate with water to make life possible. In fact, linear water molecules would be completely worthless as any kind of solvent or for dissolving anything or for harboring life at all. Many of water's physical properties derive from the fact that it is a bent shape. And we'll talk about that when we talk about water's polarity, its special type of polarity called hydrogen bonding. But for now, let's just talk about the shape. Again, why can't this be linear? I can draw it linear. Why can't it be linear? The reason it can't be linear is because you've got 4 different groups. 1, 2, 3, 4 different groups. You can't possibly put 4 different groups of electrons around a central atom in a linear fashion and expect them to get along. Each one of these groups is repelling the other ones. They want to get away from each other. And the best way for them to do that is to form, and again, this is for illustrative purposes only. There's no such thing. This is not a bond to a lone pair. There's no such thing as a bond to a lone pair. You don't connect electrons by throwing more negative charge at them. So this is only for illustration purposes. Actually, here, sorry, I meant to make this a hydrogen. Then we have the wedge up front. So think of these lone pairs as being part of a tetrahedron. The tetrahedral shape is ideal for splitting up 4 different items around a central atom. Remember, the lone pairs have an effect. They essentially help determine the shape of the molecule, but they themselves are not counted as part of the molecule. So what you have is a tetrahedral arrangement of all 4 groups. Here, let me use, 1, 2, 3, 4 different groups are arranged in a tetrahedral fashion, a tetrahedral configuration around the central atom. But when it comes to actually naming the shape, what are we going to use? We're going to completely ignore the lone pairs, and we're simply going to look at the resulting. The resulting shape is simply bent. It's simply a line bent. And the shape and the bond angles are going to be less than 109.5 because the tetrahedron has 109.5 bond angles, but of course it's going to be less than because these are going to squeeze the atoms together. Well, take this picture with a grain of salt. Just think of it this way. These 2 lone pairs are not really on opposite sides like this. They are actually, it's more like this. Actually, let me draw you another way. Perhaps even a better way to understand the way this looks. Sometimes drawing tetrahedrons like this instead, wedge and dash, I'm still using, by the way, don't feel the need to use wedges and dashes. If they are not your cup of tea, don't worry about it. You can always represent a tetrahedron simply by drawing it like this. Here, carbon, hydrogen, hydrogen. Just, if you ever need to draw them and you want to make sure it's obvious that you intend for them to be tetrahedral rather than 90-degree angles, just draw it like this. Just draw diagonals like this. And anyone will understand, okay, this person didn't want to waste their time with the so-called visual foreshortening of wedges and dashes, so they did this, and that's perfectly acceptable. Okay, anyway, that's methane. That's neither here nor there. Another way to draw a tetrahedron is to show it like this. This is exactly the same shape as the one over here. These are both the same shape. I've only rotated it so that the 2 lone pairs are, one is coming out at you, out of the board, out of the screen, and the other one is going back behind the screen, but they are both on the top, whereas these 2 hydrogens are on the bottom. And so these are squeezing. These are both squeezing the bonds together to make something that is less than the ideal 109.5-degree bond angle. They're squeezing them from the top. Think of it as these two squeezing or emanating negative charge outward and pushing these electrons. Remember, electrons are all negative, so they're repelling these electrons away from the lone pairs and thus closer to each other. Bonding electrons are less repelled by each other than they are from lone pairs. That's why the lone pairs win the shoving contest. So you end up with less than 109.5. Also try these. Again, all of these are going to have different arrangements of double and single bonds. Some of them will be only single bonds. Some of them will have a combination of double bonds and single bonds. Try them all, but notice how all of them come back to the same shape, regardless of whether you have double bonds and a single bond or just all single bonds, whether they're charged or neutral, doesn't matter. You can get the same molecular geometry from very different kinds of molecules. So that was the bent shape. Water is bent, less than 109.5-degree bond angle. Two lone pairs means you squeeze extra tight, 109 versus 120, but of course it is always less than, because less than indicates you have warped, the lone pairs are warping the ideal angle. If all of these lone pairs and bonding pairs shared the space, the volume of space around the molecule equally, around the central atom equally, then it would be exactly 109.5. Because the lone pairs seem to take up more electrical field volume or space than they really are entitled to, they squeeze the atoms together, squeezing them to less than the ideal of 109.5. All right, one last shape here. We have the trigonal pyramidal. And again, I drew a picture because again, this is another non-planar, non-flat molecule. So I thought you could benefit from a nice pretty picture like this one. Notice, by the way, in this case, I actually had my program draw in the lone pairs. I wish you could draw it as two dots, but unfortunately it tends to just represent it as if it's one more atom. But it labels it LP. LP is not an atom. LP stands for lone pair, right? LP. That's this thing right here. Again, we have our wedge, which corresponds to this over here. We have our dash, which corresponds to this one over here. And of course, we have our in-plane hydrogen, which is this one right here. So this is just a nice pretty picture. Nitrogen has its standard color of blue. For some reason, my program makes carbons gray instead of black. I think it's just because it's visually easier to see. Nitrogen has, and I chose the color for the lone pairs. I chose them to be red because I've been using red for a lot for lone pairs, but typically red is supposed to represent oxygen, but it's not oxygen in this case. LP, lone pair. Okay, so this molecule is called ammonia. Ammonia is an extremely important molecule. I want you to remember its name and its formula. Even though it's not one of the polyatomic ions, it's worth you remembering. It is one of the most important molecules on Earth. And again, makes life possible. In a different way from water, but still makes life possible, or at least it allows us to eat. Without ammonia, a lot of us probably wouldn't be here. So let's draw the molecule. Whoops, sorry about that, wrong button. Let's go with dark blue. So we have nitrogen, hydrogen, 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 and then I'll make sure that my nitrogen has a lone pair on it. Okay, so let's see, we have 5 electrons from nitrogen, and we have 3 hydrogens, NH3. So the subscript 3 indicates that there are 3 hydrogens and 1 nitrogen. That equals 8 electrons. Let's see, do we have 2, 4, 6, 8 electrons? So this is a perfectly valid Lewis dot structure. Remember, you cannot start the process of figuring out the molecular geometry without first arriving at, and even just to be absolutely sure, drawing yourself a valid Lewis dot structure. Make sure you do that. You can't just jump to molecular geometry. You have to do Lewis dot structures first. It's sequential. And then the topic we're going to cover after this, molecular polarity, derives from a proper shape or molecular geometry. Each one of these sections builds on top of the other. So you cannot do the last thing without doing the first two things. You can't do the middle part without doing the first part. It all starts with the Lewis dot structure. Then you determine the molecular geometry. And then finally, you can determine the polarity or non-polarity of the molecule, which we'll talk about in the next video, not in this one. Okay, so we have 8 electrons, valid Lewis dot structure, but once again, terrible shape. Terrible shape because, again, any structure, any picture that involves a 90-degree bond angle is dead wrong, because none of the structures we're looking at, none of the molecular geometries involve 90-degree bond angles. That is simply wrong. They are too close. And you can tell that they're too close. Why? Because 90 degrees, when I draw it like this, I'm essentially ignoring the presence of these extra repulsive lone pairs. I'm treating the lone pairs, instead of treating them as if they are very repelling, I'm treating them as if they have no charge at all, and that's just wrong. They have charge, they have repelling force. In fact, they have greater repelling force. So these are pushing away the other bonds. They are forcing the other bonds away. They are squeezing them. They are emanating negative charge that squeezes the other bonding pairs closer together, like a fist, like fingers in a hand closing together. So rather than having them at 90 degrees, instead you get the less than 109.5 degrees. Remember, think of, and again, you don't have to use wedges and dashes. Think of this as a tetrahedron. For illustrative purposes only, I'm going to make the lone pair look like it's being bonded, just like you would a tetrahedral molecule. Well, just like in a tetrahedral molecule, all 4 positions occupy space. And the only way to get them to occupy, to divide up the space, the volume of space around the central atom, is to put them 109.5 degrees apart from each other, like this. So they all take up space. But it turns out that the lone pair takes up more space because it's extra repulsive. It's not because of the physical size of the particles. Remember that. It's because of the negative charge that repels. Remember, force fields repel just as if they were physical objects, even sometimes almost more strongly than physical objects in some very rare cases. So because of that, the lone pairs actually take up more space. Here, we accounted for none of that. So because of that, we have a tetrahedron, we have a tetrahedral shape of 109.5, but when we actually look at the resulting shape, it looks like this. It looks like a pyramid. And it turns out that it's a very narrow pyramid because the hydrogens are being squeezed together. The lone pair is squeezing the hydrogens together. So instead of 109.5, you get some number of degrees less. How many less? It doesn't matter for our purposes. We just need to acknowledge that it is not the 109.5 degree bond angle that we would have expected. It is warped. It's warped because something is extra repellent. So we get a less than 109.5. It's a trigonal pyramidal shape. It's shaped like a pyramid. Remember, we do not name the shape according to the lone pairs. Lone pairs help to determine the shape, but shapes are named by ignoring the lone pairs, as if they're not even there. They are there in a sense, and they're not there in a sense. So they determine the shape by taking up space and thus pushing the atoms around, but we only look at the results of the lone pairs. We don't look at the lone pairs when naming the shape. We just see, oh, look, some invisible hand pushed all these hydrogens closer together than we would have expected, and is not letting the hydrogens occupy any space above the nitrogen. Gee, I wonder what's causing that. I don't know, some sort of ghost. Well, yeah, it's kind of like a ghost. The lone pairs are sort of like a ghost figure occupying the top of the nitrogen, or whatever the central atom is, pushing all the other atoms away, but we don't see it pushing. We just see the result. And again, also try these other examples of trigonal pyramidal or trigonal pyramidal molecules. Again, some of them, sulfite ion, phosphite ion, chlorate ion, even hydronium ion. These are all ions that you are going to have to get very, very familiar with. They are part of the list of polyatomic ions to memorize. Hydronium ion isn't part of that list, but you are going to get to know it because this is the main ion of acids. Well, other than being hydrogen ion, it's equivalent to hydrogen ion. So when we get to the acids and bases, we're going to look at hydronium ion, H3O+. So all of these are things that you're going to have to memorize one way or the other at some point or another. Might as well start now by learning their Lewis dot structures and their shapes. You won't technically need their shapes or Lewis dot structures later on, but this might help you just to sort of burn them into your memory starting from now. So ammonia, and there are others, by the way. Anything nitrogen can do, phosphorus and arsenic can do, and antimony can do as well. Anything nitrogen can do, phosphorus, arsenic, and antimony, the congeners, I realize I've never spelled that out for you, although I've mentioned it. The congeners can also, of nitrogen, can also do congene, meaning they are in the same block, they are in the same group, they are in the same family as nitrogen. So nitrogen, phosphorus, arsenic, and antimony are congeners of each other. They are family members. They are all in the same column of the periodic table. So whatever nitrogen does, the others can also do. So for example, there is such a thing as PH3 called phosphine. There is such a thing as AsH3 called arsane. And there is such a thing as antimony H3. And there is, okay. Okay, I don't know what the name of stibnium trihydride would be, so don't ask. I'm not sure. I think it would be stibnine, but I'm not totally sure. Okay, but these again, looking at these, you don't even have to wonder or work it out. If you remember the molecular geometry of ammonia, NH3, then you know that it's the same exact molecular geometry for all of these. They are all trigonal pyramidal. And that's the same is true for a lot of the other ones. If you know the shapes that are typically taken on by oxygen, and I'll give you a hint right now, oxygen almost invariably takes on the bent less than 109.5 shape. Oxygen as the central atom, it's almost always, like 99% of the time, bent less than 109.5. Well, guess what? Sulfur does a lot of the same things as long as there's only two atoms attached to it. Selenium, tellurium, same thing. They are congeners of oxygen. They tend to form the same kinds of molecules with the same kinds of molecular geometries, again, given the same number of outer atoms. Sulfur dioxide and ozone, there aren't a whole lot of bent shapes with less than 120. In fact, other than the ones I've got listed here in the sulfur dioxide, the only other ones are more theoretical or more hypothetical than realistic. These are probably the only ones that I could find that are actually real molecules or real ions. Likewise, methane, carbon, well, carbon is very flexible. It can be either tetrahedral, trigonal planar, or linear. Linear examples are not that common. Trigonal planar are quite common, but the most common is tetrahedral arrangements for carbon and for all its its two congeners, silicon and germanium. These also tend to form the same kinds of compounds as carbon. Similar compounds. So if you have the same number of atoms on the outside of silicon or germanium, you have the same shape that you would if you had carbon. The only thing under boron is aluminum, which is a metal. So we're not typically going to look at compounds with aluminum as molecules, but instead as ionic compounds. Okay. Carbon disulfide, again, this is one of those examples where the carbon is linear because it has two double bonds. But again, that's not all that common. In fact, there are only two examples, carbon dioxide and carbon disulfide. The only other linear example is hydrogen cyanide, which I have listed down here. Other than that, you're not going to see too many linear carbons, at least not as a simple molecule with only two outer atoms. You will see extended chains of carbons where one of the carbons is linear, or two of the carbons are linear geometry. I believe the practice has one example of a linear triple bonded carbon that is linked to fluorine, and it looks like this. It's two fluorines attached to two carbons. Here, though, the difference here, and the reason I'm not going over this too much is because there are two central atoms. Both carbons are considered are sort of like central atoms. So two central atoms. Occasionally, we are going to look at molecules like that. But again, I will always make it very obvious what the structure should look like. If I'm asking you for that, I will give you hints because in this class, we don't really go into these types of molecules that much. So I will let you know what the arrangement is. If I don't say anything, then you can assume carbon is the central atom, or whichever atom you have only one of is the central atom, as long as the others are multiples. Okay, so next up after this, once we know shape, we can determine something called molecular polarity. Polarity would be whether a molecule has what's called a net dipole, or whether all the dipoles cancel each other out, or whether any of the bonds that form a molecule even contain significant dipoles, significant differences in electrical charge, what are called permanent dipoles or no permanent dipoles. So we'll take a look at that next, but we are going to build on molecular geometry in order to make that determination. So first we start with Lewis dot structures, then we go to molecular geometry, and then finally we can use the molecular geometry to figure out a molecule's polarity or non-polarity. And that determines the physical properties and sometimes even the chemical properties of molecules. A polar molecule versus a non-polar molecule will have radically different physical properties like boiling point, density, melting point, volatility, surface tension, and other kinds of physical properties that we associate with a molecule's stickiness. We'll talk about that in a future and actually future set of videos. Advantage of the extra practice or extra examples I've provided for you for each of these different molecular geometries. They are well worth your time to try. And just recognize that congeners of the same central atoms will typically form the same types of molecules. So that's a little bit of a shortcut for you if you realize that. Because all that really matters is the number of valence electrons in determining shape, or in determining the Lewis dot structure, which determines the shape. Okay, so give it a try. Let me know how it goes. Hope that was informative. I will see you in the next video. Take care, everyone.